Okay, in this video we're going to talk about an important topic, which is the isothermal process, and also the other kind of iso process as well. And how do we use the thermodynamics first law to calculate related um, energy in this process? The energy that we are going to focus on this part is going to be the internal energy. Previously, we have another video talk about work, and before that we talk about the Q, which is the heat. So now we are going to focus on the internal energy. So you can change the internal energy in two different ways. As you can see in our equation over here, right in the middle, the change of U, that U represent the internal energy. Now be careful, the U and delta U are different. The U itself is just simply simplify the internal energy, and that energy is simply just the particle energy inside of the element. Each one of the element is not actually fixed, they are moving all the time. If they are moving, then their energy is what we call the kinetic energy. So the kinetic energy inside of the element is what we call the internal energy. The change of internal energy meaning you have to change from one place to another. Where in a gas, we are not talking about from one place to another. We simply said the gas is changed from one state to another state. And what does that state means? What a state means, what is the condition of the gas? And that condition include the pressure, the temperature, and the volume. So these temperature, volume, and the pressure are what we call the state variables. This state variable change will change the state of the gas. So if the gas at the 1 atmosphere pressure in 1 meter cube is going to be different from like 2 atmosphere pressure and 1 meter cube volume. So that is the one that you're going to define how the element is. And the internal energy is defined by these states as well. We're going to see that in some of the example later. We also going to mention about the second law of the thermodynamics, and it is related to a terminology called entropy. You probably heard about this in chemistry. We have actually a way to calculate entropy as well. So these are the topic for this lecture. For the next exam, exam 3, one of the question is going to be similar to the picture that you see right now on the screen. We are going to give you a PV diagram, and we will ask you to calculate either the state of the gas, or if the gas goes through different process, then can you figure out what is the Q and what is the W related to these processes. What are the processes that we can define? Well, let me just look at the process first, then we'll go back to the Newton's the thermodynamics first law. So here that you can see the isoprocesses. So the isoprocess are the process that you can move from one to another. So if you move from one state to another state, and depends on how it moves, and then it will have a different process. There are 4 different kinds. There's isothermal, isobaric, isochoric, and adiabatic. Each one of the process will have something either fixed or equal to 0. When you have an iso, simply means something is fixed. So thermal kind of represent the temperature, so isothermal represent temperature is fixed. When you have a baric, that represent a pressure, so isobaric meaning the pressure is going to be constant. Doesn't matter how you change, pressure keep at a constant. Similarly, caloric represent the volume, so isocaloric V is a constant. Adiabatic meaning there's no heat transfer in and out, so you're isolating the gas in a chamber and nothing, no heat will transfer in and out of the system. So Q is equal to 0. So these four, you have to remember what does that mean. Now, based on different condition, you're going to have certain things is going to be equal to 0, and certain things you can calculate based on the thermodynamics first law. Let's go back to the first law over here. So this one here is our first law. The first law has the equation to relate the change of internal energy, and that is related to our heat and also the work. So if you give the heat to a gas, just by thinking of that, you certainly know when you add heat to the gas, you are going to increase the internal energy. So this Q is going to proportional to the internal energy change. The internal energy change meaning the final internal energy to the initial internal energy. So that's why we write the use of F minus the use of I. And the I represent the initial, F represent the final. Okay, so if you add a heat, you can change the internal energy, and it's going to be a positive change because final is going to be larger than the initial. And be careful about all this subscript. This subscript is important because it might change the sign of your value over here. The Q here represents the environment to the gas, which means you are adding the heat into the gas. Well, if this number is negative, what I mean is the environment is going to take the heat out of gas. That's what a negative means. So it determines the flow of the heat, how it flows. Is it flow in or flows out? The next one will change the internal energy is the work. So work, as we learn in the mechanics, the work is due to a force and times the displacement. Now over here, the previous lecture video, which is important, you should watch that to understand how the work is calculated. It is based on the P times change of V. So P represents the pressure, change of V represents the volume change. If you want to use this equation, and this equation is actually based on our definition, the F times the change of X. So look at here that we have a force times the change of X, which is the displacement. If we multiply this whole equation with an A, then we divide with an A, which is the area, then we didn't change the F times delta X. And then you recognize if you have F over A, it is simply the definition of the pressure, and the area times the change of X is our change of volume. That's why this P times delta V is coming from. So you can calculate work based on force times displacement. It's also equal to pressure times change of volume. Now the thing I want to emphasize before we actually do some example is the subscript. Again, the subscript is important because it determines where the heat is flow in and out, or the work is done by certain things to another things. If you write this one as negative sign Q minus W, this minus, when you use minus, that represent is the work done by the gas to the environment. or it's due to the gas on environment. So that we are looking at how the gas is doing the work to the outside. Then you put it negative. On the other way, if you write positive, then W should be the environment to do work on gas. So the sign is important. A lot of people make mistake during the exam simply because they mess up with the sign over here. If you stick with this equation, and especially, so if you go to the study guide for the exam 3, there's a formula sheet. Just make sure that you, if you don't remember, just write down the notes to remind yourself how you make this one to be positive and negative based on the subscript. So let's look at this PV diagram, to use this PV diagram to explain. Over here, this represents the PV diagram where you have x-axis represent volume, y-axis represent the pressure. As we said, the state of the gas is determined by the state variables. And we have pressure, we have volume, we also have temperature. How do we represent temperature in this diagram? Well, the temperature can be represented by the two black line, two curved line that you see over here. So we have one line more like an inward toward to the origin, the other one is going outwards. And these two we can represent with a different temperature. If we look at the temperature of point A, so point A is this point over here at the lower left corner on the T1 curve. So if we look at the temperature at point A, and we can find out at the point A, the state is determined by the V1, which you go down, you can find the volume of that. And you can go horizontally to get the pressure of the point A, which is a PA. If this is an ideal gas, then we can actually use the ideal gas law, which is a PV equal to mRT, to find what this temperature is. So if you look at the right hand side, we have at point A, the gas has a volume V1 PA, and the temperature, let's say, is T1. Then we can relate this by the ideal gas law. We can write down the T1 is equal to PA V1 divided by M times R, where N represents the number of mole, R represents the ideal gas constant. The value of the R depends on the unit that you are using, so be careful when you use this constant. Normally we use 8.314. That you have, if you use the mole as the N, and you use the meter cube for the pressure, for the volume, and the pressure to be Pascal, then this R is going to be 8.314. So this one you can get a temperature of 1. On the other end of, on the right hand side, you can see another point that will mark as a C. The C point is on the second curve, where the second curve has a different temperature. The temperature is T2. We can actually calculate the temperature of T2 with a similar way using the PV equal to mRT. So PV equal to mRT also give another temperature T2. The T2 will be PaV2 over M times R. Notice that the P is the same because they are on the same level on the y-axis. So they have the same pressure, however they have a different volume. And because they have a different volume, so their temperature is going to be different at the same pressure. Now we wanted to determine which temperature is larger, because you have two different temperatures represent two different curves. And just look at these two equations, the T1 and T2 equation. You can kind of see the T, if P is a constant and R are also constant, then temperature depends on the volume. The larger the volume, the larger of the temperature. Based on this, the T2 should be greater than T1. So if you have another curve going outwards to the T2, then the temperature T3 will be even larger than the T2. So that is how you can determine which one is a larger temperature, which one is small temperature. And just by looking at the PV diagram, you can also calculate the temperature as well. I want to remind you this temperature over here is a temperature in Kelvin. It's not in Fahrenheit, it's not in Celsius, it is in Kelvin. So make sure that when you use this one to do the calculation, whatever the number that you get is in Kelvin. If we ask you about the temperature in different scale, then you have to know how to do the conversion, how to change it to the Celsius, how to change it into the Fahrenheit, and there's an equation in your formula sheet as well. So make sure that you have that formula sheet ready and know how to do the conversion. All right, so that is the T. Now let's look at something else. Let's look at what this process means when you look at the different state. Now it's very easy to identify which process that is. First, we look at A to B. So A to B, A and B is right above the A. And if you look at the PV diagram, you can see if you move from A to B, the volume doesn't change. The volume keeps at the V1. However, the pressure changes. And temperature also changes as well because they are on a different curve. So you keep the volume to be fixed, but you allow the pressure and the temperature to change. So what kind of process that will be? So volume is a constant, and you look at the right hand side, volume is a constant that represents isochoric. So this is an isochoric process, and the volume is a fixed number. When the volume is a fixed number, if we wanted to calculate work, and what would the work is going to be? Now you look at the equation. Work is the P times change of volume. Okay. Now, without looking at the pressure, if you look at the change of volume, our initial volume is at the A, the final is at the B. That change of volume simply equal to 0 because volume is a constant in this process. So there's no volume change at all in this case. So isochoric, the work is going to be equal to 0. Okay, remember that is an important conclusion that you can use to calculate that in the future. Adiabatic Q is equal to 0. So that is another one that we know. So this one, let me write it down over here. Isochoric work equal to 0. Let's look at another process. Let's look at the process go horizontally from A to C. So from A to C, we keep pressure to be this constant, but volume change, temperature change. So pressure as a constant is called isobaric. Pressure is a constant. Okay, pressure is a constant, and that's isobaric. If pressure is a constant, then how do we calculate work? Well, if pressure is a constant, and it's actually easy for us to calculate work, this is a P, and that change of a volume will be the V final minus V initial, right? That's just based on the change of volume. Then you can calculate work. By looking at the graph, now this one is going to be V2 minus V1. Okay, it might have a different value, but you can read the value from the PV diagram and just simply put the value into the equation and you can find out the work. Again, this work is the work done by the gas to the outside. So it's gas on environment. Okay, what about isothermal? The isothermal can also give us work. Now, without derive the equation, well, however, for the honor section, I will give you another video that you are responsible to know how to derive this equation. For the isothermal process, work can also be calculated, and that is based on the ideal gas law. When you have an isothermal process, the work will be a nature log. This one is going to be equal to mRT, if you know the temperature at that state, times the nature log of V sub F over V sub I. Okay, so isothermal work is equal to mRT. The T is the temperature, and because you change from one state to another, and their temperature is the constant, so it doesn't matter which temperature is the same temperature anyway, and times the change of volume. So what is the isothermal process in this diagram? In this diagram, from B to C is an isothermal process. So if you move from B to C, the arrow will be in this direction. Then the isothermal process is going to be equal to, the work is going to be equal to this. In this case, this will be T2 because we are looking at the curve of the T2. And the volume of the final is going to be V2 and the initial will be V1. So that's how you calculate work for different processes. Okay. For adiabatic, we don't know. We don't have a work. We only know the Q. So the Q is equal to 0. But we can calculate the work in an indirect way. What an indirect way is, we know that the first law is always valid. So if you can find out the change of internal energy, and you know this one equal to 0, and then you can know that change of internal energy is simply equal to negative work. So even though there's no equation to get the work of the based on the P and V, but we know when you have an adiabatic, the work is simply equal to negative change of U. It's negative change of internal energy. Okay, so these four equations is important for you to calculate the internal energy to calculate the work based on the process that you're looking at. Alright, so another thing we wanted to look is what about the Q? So we talk about the work, we talk about, so now let's look at the Q. If you have a Q which is not adiabatic, then you're going to have a value. So this value has two different situations. If you are isobaric, you are isochoric, their Q is going to be different. And you can read the material 15-4. I'm not going to spend time to explain that. And you can watch the video from the Khan Academy as well. They explain about these two. I just wanted to show you these two equations and point out the important thing you have to be careful. The equation is very similar to the equation that we calculated in the calorimetry. When we calculate calorimetry, we calculated the Q due to the change of the temperature. This is also due to the change of temperature, and it's based on the M, which is the mass, times the C is the specific heat, then times the change of temperature. It has a similar form, but it's not using the mass. It uses N here. N represents the number of mole. So therefore, the C over here actually is a capital C. Is defined differently. It's not the same as the small c. Small c represents specific heat. This C over here is the capital C. This represents the molar specific heat. It represents how much of the more, if you have how much heat needed to change the temperature of 1 degree for 1 mole. So that's the capital C represent. For isobaric and isochoric, the C will be different. So that's why you see the CP and CV. There is a relationship between the CP and CV. Their difference is difference of R and R. The R is 8.314. So you can also relate these two. The CP is greater than the CV, meaning if you wanted to change the temperature by 1 degree for 1 mole, you need more of the heat when you want to keep the pressure to be constant, as opposed to that you keep the volume to be a constant. So that is what this 2 means. This 2 tells you how you can relate the CP and CV. Therefore, if you wanted to calculate the Q for these 2 processes, isobaric and isochoric, then you can use these 2 equations to get it. I also have the W, which we can get the work. And then you can find out what is the change of internal energy. Right, so this is how you can use this equation to do the calculation. Again, I wanted to remind you these are very important equation, and I hope after this video you will spend some time to review this, and when you work on the homework or work on a similar problem and you don't remember how to do that, you should go back and watch this video again. And this is definitely going to be one of the problems that you're going to see for the exam 3 and possibly in the final exam as well. So you better to spend decent time to look at this. I wanted to look at one more thing about the PV diagram. Whether the one more thing is, we talked about the Q, we talked about W. Now the last thing we wanted to discuss is the U, internal energy. Internal energy is actually represent how much of the temperature of the substance. If you have a pure ideal gas and it's atomic, which means you only have 1 atom, then this internal energy is equal to 3 over 2 N times MA K times T. Each one of these represent different things. The N small n represent the number of mole. The MA represent Avogadro number, 6.02 times 10 to the 23. K here represent the Boltzmann constant. Boltzmann constant is another constant. In the exam, we will give you all these constants. The T over here represent temperature. Again, this is in Kelvin, okay? Don't just use Celsius. A lot of people make mistake. Didn't pay attention to the scale or the unit, then you are going to get the wrong number. So this is a U. Now, we are looking at a change of U. If you look at the change of internal energy, then you have a U2 minus U1. Then U2 will represent a different temperature, U1 will be another temperature. If you write this equation to represent the U, you will find out the change of internal energy is equal to 3 over 2 N times MA times K. These are all constant. All these are constant. The only thing actually changed the internal energy is the change of temperature. It's T2 minus T1. Right? So when you have a change of temperature, you change internal energy. Therefore, you can simplify this one to be 3 over 2 NMAK change of temperature. This can also can be also expressed as the 3 over 2 MR times change of temperature. Okay, so these two equations are the same. Are the same. Okay. Now, let's start to look at some example over here to show you how you can use those ideas that we introduced. The first example that we have is we have two more of ideal gas and expand adiabatically. So again, adiabatic meaning Q is equal to 0. Performing a work was 8,000 joule. This work is the work from the gas. Is a gas down on the outside, the gas to the environment. So this 8,000 represent gas to the environment. Again, I emphasized once a lot because the subscript really matter. You have to look carefully about what the problem gives to you. If they write this work is from the environment to the gas, then you have to use the different sign for the work. If you use this the first law, which is the equation that we write in here, change of a U is equal to the Q minus W, and this one is the W. 8,000 is the W in this equation. And we want to find out what is the change of the T during the expansion. Now, this equation doesn't have a change of T, but we just tell you the change of U is equal to this one here. So you can write this one, which is a 3 over 2 and R change of T. Then you can find out what is the change of T. The Q is equal to 0 because it's adiabatic. W is given, which is 8,000. So you put 8,000 here, and that is equal to 3 over 2 mR change of T, which is over here. Then equal to negative 8,000. Then you can find out change of temperature is equal to this. And the result is going to be in Kelvin. Negative 321 Kelvin is the result. Okay, so I'm going to record probably another example, or we're going to do another example in the exam review section. So make sure that you understand and make sure that you know how to calculate this. And again, I couldn't emphasize more. In your coming final exam, you are going to, I'm assure you, you're going to have one problem similar to this. You're going to give it with a PV diagram. You have to do a whole bunch of the equation to calculate the heat, the work, the internal energy based on this idea. Another question you are expecting for the coming exam is going to be the Q, which will be based on the Newton's zeroth law thermal equilibrium. So you have to know if there is a change of temperature. In addition to that, you have a change of the state. I did record a video to show you an example of that. You should watch that as well. So these two questions will be on your coming exam 3. I hope everybody will get it right this time. If you didn't, that simply say that you didn't even watch the video. So I hope that you do spend decent time on these two questions. Alright, I will see you next time.